Hello and welcome to the Daily Space for today, Thursday, July 23rd, 2020. I'm your host, Dr. Pamela Gay, and I am here to put science in your brain. I would like to start today's episode by congratulating China for launching their first solo mission to Mars. This is the second major launch of this launch window to Mars, and coming up on July 30th, we hope to see the launch of NASA's mission. But with hurricane season in full swing, we're all holding our breath a bit to see what actually happens. Looking a bit farther out in the universe than Mars, we'd like to share that astronomers using the Very Large Array Radio Telescope in New Mexico have mapped out the powerful magnetic field in the Edge-on galaxy NGC 4217. This system is about 67 million light years away, which makes it close enough to readily observe details. Using multiple techniques to detect magnetic fields, this team was able to observe an incredible X-shaped structure that extends as much as 20,000 light years from the galaxy's disk. They were also able to detect bubbles associated with supernovae and an unusual magnetic helix structure. Magnetic fields can align light waves, so they have specific polarizations that can be filtered with telescopes. By looking at how much light has what kind of a polarization, the magnetic fields can be mapped out. According to Rainier Beck, it is fascinating that we discover unexpected phenomena in every galaxy whenever we use radio polarization measurements. Here in NGC 4217, it is huge magnetic gas bubbles and a helix magnetic field that spirals upwards into the galaxy's halo. Beck is a co-author on a new paper appearing in Astronomy and Astrophysics with lead author Yelena Stein. Stein goes on to add, "This has never been observed before. We suspect that the structures are caused by star formation, because at these points, matter is ejected outwards." Magnetic fields are one of the harder things to understand, one of the harder phenomena in our universe to understand. And exactly what causes the magnetic fields in galaxies is still a bit curious. We know in general that ionized particles that have some sort of an additional charge when in motion can generate a magnetic field. This implies that plasma, clouds of energized material, or rather clouds of ionized material in galaxies spiraling throughout the galaxy as they orbit, are able to generate galaxy-spanning magnetic fields. Also, the motions associated with gas getting accelerated out during supernova explosions can also generate magnetic fields, as is observed in this case. Studying this galaxy-spanning magnetic field is the kind of careful, no luck required detail work I love. A research team simply goes and says they're going to look for something. They get their telescope time, they do their science, and results prove or disprove that, well, they've seen what they hope to see. Not everyone likes this kind of predictable way of doing science. For those who like things on the wild side, we have supernovae. Back in December of 2019, the Zwicky Transient Factory was able to pick up a new supernova named SN 2019 YVG. This particular system was quickly turned to by a myriad of different telescopes, including NASA's Neil Gehn Swift Observatory. And it was with Swift that an unusual UV flash was observed. In general, UV flashes are thought to occur, but aren't generally seen when white dwarfs explode as type 1a supernovas. Here, they had amazing luck, and they were able to see something that had never been seen before. Now, with this particular system, Um, the UV flash could mean a number of different things. And we're having a technology issue. I'm sorry. I'm going to have to pause here and you're going to have to edit the video, Allie. For whatever reason, my notes just like don't include all of the script. And I don't know what's going on. I downloaded it and it just didn't come through the way it was supposed to. I'm sorry, everyone. The deep, dark secret of this is that we're working from a script. And when the script doesn't update correctly, things go boink. I'm watching my device update the file. Come on, you can do it, little device. You can do it. Maybe you can't. All right, I'm going to pull this up elsewhere. Good times with technology. I'm so sorry, Allie. I am so very sorry. Let's set the iDevice over there. Let's open up my notes over here. There we go. I don't understand. The notes are on the one device, but let's see if I can get them to download again. Okay, I see what's going on. All right, we're going to be good to go in just a moment. Let me find where I was. Just a moment. All right, so all right, I now have control of my device again, and I'm going to start over from scratch talking about this particular supernova. Spotted in December 2019, supernova 2019 YVG was discovered by the Zwicky Transient Factory, which turns up supernovae on a regular basis. What made this one unusual was a UV flash that was seen with NASA's Niels Gehr's Swift Observatory. As happens with many different supernovae, a variety of telescopes around the world turned to see just what this particular explosion might have to offer. It turned out it was just a almost regular everyday type 1a supernova, the kind of supernova that comes from a white dwarf star hitting a critical amount of mass and exploding. Now, in these new results published in the Astrophysical Journal with lead author Adam Miller, they document that while it's long been understood that exploding white dwarfs could have ultraviolet flashes, it's only been seen one time before. This kind of a UV flash is rare, and time should literally tell us what exactly happened inside this particular explosion. And the reason I say that is shortly after a supernova goes off, the cloud of gas and dust surrounding the supernova is extraordinarily dense. But over time, it expands outward and thins as it does, allowing us to see deeper and deeper into the system to actually see what remains. According to the press release, Miller and his team believe this will offer us an important clue into understanding why white dwarfs explode, which has been a long-standing mystery in the field. Currently, there are multiple competing hypotheses, and Miller is particularly interested in exploring 4 different scenarios, which match his team's analysis for Supernova 2019 YVQ. The potential scenarios that could cause a white dwarf to explode with an ultraviolet flash are: the white dwarf consumes material from its companion star and becomes so massive and unstable that it explodes, and the white dwarf's expelled material and the companion star collide, causing a flash of UV emission that isn't there in every situation. It could be that extremely hot radioactive material in the white dwarf's core mixes with its outer layers, causing the outer shell to reach higher temperatures than usual. It's a fluke of how it explodes. It could be that the outer layer of helium ignites the carbon within the white dwarf, causing an extremely hot double explosion and this ultraviolet flash. And it could also just be 2 white dwarfs that are merging, triggering an explosion with colliding ejecta that emit ultraviolet radiation. There's lots of possibilities. And what's cool is they make specific predictions on what can be seen. According to Miller, within a year, we'll be able to figure out which one of these 4 is the most likely explanation. Our abilities to image things improve, allowing us to discover more and more about our universe in 2 different ways. We can build bigger telescopes that are capable of gathering more light and seeing both fainter objects and resolving smaller objects. We can also just build better and better cameras that capture light more effectively and take full advantage of the telescopes they are mounted on. When a great telescope is combined with a great camera, wildly awesome things are possible. In my honest opinion, there is no better telescope than the European Space Agency's Very Large Telescope, and its Sphere instrument is arguably one of the best cameras out there. Working together, this system has captured the first ever image of multiple exoplanets orbiting a star. This stunning image is of TYC 8998760-1. And it appears in a new paper in the astrophysical journal Letters with lead author Alexander Bond. According to Bond, this discovery is a snapshot of an environment that is very similar to our solar system, but at a much younger stage in its evolution. Co-author Matthew Kenworthy goes on to add, even though astronomers have indirectly detected thousands of planets in our galaxy, only a tiny fraction of these exoplanets have been directly imaged. Direct observations are important in the search for an environment that can support life. This image captures 2 gas giants marked with arrows that are orbiting at a distance of 160 astronomical units and 320 astronomical units from their star. Now, for comparison, our solar system's Kuiper belt appears to end at about 55 astronomical units, or 55 times the distance from the Earth to the Sun. This is roughly 1/3 of the distance of the nearer of these 2 worlds to its star. This isn't a solar system-like system. It's spread out a whole lot more. But it is amazing that we can just image it. According to Bond, the possibility that future instruments such as those available on the Extremely Large Telescope will be able to detect even lower mass planets around this star makes an important milestone in understanding multi-planet systems, with potential implications for understanding the history of our own solar system. Right now, we can only hope that our telescopes and technology advance so that solar system-like systems will become observable. Looking for worlds in distant orbits from their stars is hard work. These 2 gas giants could be directly imaged, but Most of the time, our only hope for seeing worlds is to catch them crossing in front of their stars and blocking starlight in a way we can observe. Today, this kind of discovery is the job of TESS, which is orbiting our planet, and the job of a myriad of observatories here on the surface of the planet Earth. Now, unfortunately, one of the limits of TESS is that it only looks at individual fields for 27 days at a time, which means that it can only catch objects with extremely short orbits, because to see that there's a world out there and actually understand where it is in its solar system, you have to see it go around its star more than once, ideally 3 times. Now, unfortunately, this means that we can't see worlds like us. We can't see worlds like Venus. We can't even see worlds like Mercury. And so folks are trying to find a new way, because TESS is observing single dips that seem to indicate worlds with orbits longer than that 27 days, or just ill-timed, so that while they may have a 27-day orbit, we only catch one of their dips. Helping out to rescue these otherwise lost worlds discoveries is the Next Generation Transit Survey in Chile, which is shown in this image. It's starting to follow up on these lost worlds, and in a new paper in the Astrophysical Journal Letters, it documents their first discovery of NGTS 11b. It's a warm Saturn that orbits every 35 days. This still isn't Earth. It still isn't even Venus, but it's a start. We have a long ways to go to see longer orbits. I don't know when the tech will get there, but when it does, we'll bring you the discoveries here on the Daily Space. But for now, 35 days is something to be excited about. This has been the Daily Space.